Hi everyone. In this lesson we are going to discuss combined loadings and its effects on the stresses and stress states on any point on the structure that we analyze. Take two samples here, two rectangle cross-sectioned rods. They are the same size. You see it is schematical drawing on the paper. I'm going to load one of them as shown on the image here, and I will load the other one right from the corner, and it will become like a cantilevered beam. If I hold from here, this is a cantilevered support rod. This is a rod with a rectangular cross section, and at here it is cantilevered supported. So I hold one of them and load from the corner, the other one same support but load from the very tip, and compare the failings. And then we will carry on to the calculations, and we will deal with the stress states at any point on the rod. Let's start with this. I will load this, hold it from the beginning, from here. You see the dimensions, 60 mm here, 40 mm here. So if I hold it, if I load it from the tip like this, it will behave like a beam. You remember the cantilever support beam. Okay, let's load it and see what will happen. I applied load. It hasn't failed yet. Yeah, it now failed. Okay, you see this is the failed cross section. Okay. By looking at the cross section, you can imagine what type of stresses had happened in the cross section. Okay, this one was like a cantilever support beam. Okay. If I'm going to draw the loading condition for this beam, or for the rod, so it is the rod here. I loaded it from here, and it is fixed. Okay. So if I load it from this point, we look at it from the side, just like a two-dimension. So why did it fail from very near to the support? It is because the maximum moment occurred here. So we have zero moment around where the load is applied, and maximum moment here, because force is the same. If we multiply it by the larger force distance, we get the larger moment. Therefore the largest moment is where the largest force arm is. It is here. So M is, say if it is P, M is equal to P times force arm is 60 mm. So it failed here. What else is there? There is also transverse shear happening in the cross section. Some bending moment and transverse shear. And this failed mostly due to the bending loading. There is a little effect of the shear stress, but the majority of the fail is caused by the bending stress. We discussed this in the previous lessons. Okay, now going to the other rod, and do the loading like as shown in this picture. So holding it like this again, representing the fixed support, cantilever support here, and the other end I apply the load. Or should I show like this, or doesn't matter? Okay, loading it. Yeah, now this is the fail. I just separated for you to see the cross section clearly. I separate from the very bottom that there is the 99% fail on the cross section, don't worry. Okay, this is the failed cross section. You see these are quite different. This one is almost flat, this one is not flat, this is like a, this fail is in 3 dimensions. This is, if we take look at this coordinate system, the fail is in YZ axis for such kind of loading, but when we load like this instead of like this, the cross section is fail in the cross section is in 3 dimensions. We can see the fail in X, Y and Z axis. Okay, so here we see the effect of combined loadings. Okay, this fail, there is actually this fail is also partially due to 2 different loadings, 2 different stresses, as we talked before. One is bending stress, the other is shear stress. But the combination is minor here. But here there is the 2 or 3, at least 2 major contributions from 2 different stresses for this state. Therefore, for such kind of loadings, we say combined loadings. Okay. We will see why this happened when we do our calculations on this image here. This is the image of the same rod actually, but we will do a quantitative analysis here. This one was a qualitative analysis, but now we will do a quantitative one. Okay. By dealing with the combined loadings, and we can find or determine the stress state at any point on this rod. Let's choose a point here, or which point should I choose? I choose a section first. This section, let's say this section is 20 millimeters away from the fixed support. This section is 20 millimeters away from the fixed support, and say that the point of interest is 15 millimeters from bottom of the cross section around here. So it is just 15 millimeters away from the bottom of the cross section and 0 on the right. Okay, let's call this is point A, and what we want to do is to determine the stress state at point A. Okay. What we are going to do first is to determine the internal loadings on this section. What do we do in order to find the internal loadings at a section? we first cut the piece, the part at that section and obtain two segments. So if we cut this into two pieces, the segments we get, the one on the left is this, the one on the right is this. Okay, and what I want to do after determining the internal loadings at this section is to proceed to determining the stress state at this point. This point is here and here. It is the same point. It doesn't matter. So, starting with the internal loadings, we pick one of the segments. Which segment should I pick? I should pick this one because there is the known external loading here. It is P. Okay, and I don't know the external loading at this end of the segment because they are reaction loadings, and I don't know what they are. So in order to avoid additional calculations, I prefer to deal with this segment. Let's give a number for point P, for the load P. What can we say for that? Let's say 10 kilonewton. P is equal to 10 kilonewton. In this case, what would be the internal loadings at this section? I draw the free body diagram of the segment on the left. Distances, I need to plot the distances as well. This one is 40 millimeter. This one is also 40 millimeter because I cut from the 20th millimeter from the right. So the 40 millimeter left on the left segment. Okay, now what loadings will act on this section? So there is internal loading on this part, on this section. Okay, the internal loadings here. What are they? First, there is torsion, right? There is torsion on this direction because we applied 10 Newton, not 10 kilonewton, it is 10 Newton. We applied 10 Newton load like this. Okay, let's make a cut from the 40 millimeter. Okay, two segments, as in here, two segments, and we were interested in the stress state here. Okay, it is the same point, and we cut the piece from the section of the point, and we have drawn the free body diagram here. Applying the 10 kilonewton load, what will happen is the other side of the segment will apply a reaction to the opposite to this rotation. Okay, it is a torsion effect, we apply 10 kN load. The other side here is trying to pull it back, rotate it in the opposite direction, so that the whole part is in static equilibrium, right? Applying load, so this one is trying to rotate the other side. So the T torsion is equal to 10 times, what is the force arm here? This one, 40 millimeter, is the force arm that causes the reactional torsion, 40 millimeter. Therefore, the T internal T is 400 Newton millimeters. So we have found one of the internal loadings at the section. What else is there? So one is torsion effect. The other is bending effect, right? As well as torsion, there is bending, which causes the section bend like this, and the axis of bending is this. So this is the axis for bending. For the torsion, the axis is this. So it is x-axis. Therefore, T that we have written here, it is for Tx actually. So we should say Tx is 400 Newton millimeters. And moment, this is the moment axis. As you see, applying the load. So what happens? The other section, the internal loadings that we plot here is the loadings coming from this face of the segment. So the torsion was like this, Tx, and bending, you apply this, and this segment causes it to bend like this. Okay, therefore the my we put in this y, because this is y-axis. My is equal to, and the direction is this, it is equal to 10 times again the 40, because this is the force arm for this axis. 10 times 40 again. My is equal to 400 Newton millimeters. What other internal loadings might there be in this section? So applying the load, we have also shear. You see, if I apply like this, there is bending, torsion, also shear, because I am pulling this segment down and the other segment is pushing it upward. Therefore, there is a shear in this direction, and I can say Vz for the sub-index Z, because it is in the Z axis. Vz is equal to the same magnitude of the external loading, 10 Newton. Yeah, now we have determined all the internal loadings on the section. It doesn't matter which section you deal with. We can look at here, we can look at there, doesn't matter, but since we see when we cut like this, we see this face, therefore we would prefer to deal with this face. And if I pull up this face, and point A here. The internal loadings are the same on the opposite face, but the same magnitude, but the directions are the opposite on the opposite face. Therefore, the internal loadings I want to show here are in the opposite direction. So if my was like this, in this case my will be like this. This is y-axis, this is z-axis, sorry, x-axis, this is what z-axis. Y-axis. Okay, and this is my, opposite to this direction, 400 Newton millimeter, and Tx is also in the opposite direction. It is again 400 Newton millimeters, and Vz, we are talking about this face, don't forget. Vz is downward Newtons. Now we have determined all the internal loadings on the cross section where the point A is. Okay, what we are going to do next is to determine the stresses that acts on this point. Looking at a closer look at the point A, point A was here. If I want to determine the stress state of a point, I substitute that point with a cube, okay? Because we do all our mathematical calculations, all our analysis in mechanics in 3D. Therefore, we substitute the point, which is a zero-dimensional object, by a three-dimensional object, which can be a cube. Okay, here the cube substituted. That substituted the point. Instead of a point, there is a cube. And what did we have on this face? On this face, we had a shear force V, but the Vz we have found, it is an average shear stress on the surface, on the cross section. Sorry, shear load, average shear load. If I want to determine the shear stress at this point, you remember the formula. Tau equal to V average times first moment of area divided by area moment of inertia, or in other words, second moment of area times thickness of the cross section. V average is equal to 10 Newton. I, we can calculate I by using the formula BH cubed over 12. T is 15 millimeters. Here it was 15 millimeters, therefore the T is equal to 15. And we can calculate Q. What was the Q? Q is the first moment of area about a line. So point A is here. The line where the point A is on is here, and it is 15 millimeters from the bottom of the section. So I can determine the first moment of area by using either this area or this area. They will give off the same result. So what is the logic of the first moment of area? It is multiplying the area, say this A1, A2. If I pick A1, I multiply A1 by the distance between the neutral axis of the whole section. The neutral axis here is 10 millimeter away from the bottom of the cross section, and the distance between here and here, which is the centroid of A1. And what is it? 5 here, 2.5 here, so 7.5 millimeters. So the distance between the centroid of A1 and the neutral axis is 7.5. Therefore Q is equal to 7.5 millimeters times A1 is equal to 15 times the height is 5. It is equal to 75 millimeters squared, and it is equal to 7.5 times 75, 562.5 millimeter cubed. Okay, we determined the average and we know what T is. Calculating the I is equal to, I applies the whole cross section, BH cubed over 12, 15 times H is 20 cubed over 12. It is 10,000 millimeter to the power 4. In this case, tau is equal to 10 times 562.5 over 10,000 times 15. Tau is equal to 0.0375 Newton over millimeter square. This means tau is equal to 0.0375 megapascal, and converting into kilopascals, it is 37.5 kilopascals. So the shear force acting on the point A is 37.5 kilopascals. So here it is not V, we plot it by tau. 37.5. If we have got 37.5 kilopascal shear stress on this face, there is a complementary shear stress on the top face. So this is the same shear stress. Also on the other faces that we don't see. And the next, we can determine the bending stress. Bending stress at point A, because here there acted also a bending stress. Remember here, this one, which one? The one around y-axis, there is bending stress. And how do we determine the bending stress? Sigma is equal to m times c over I. M is the moment acting on the section. We determined it as 400. C is the distance of the point of interest to the neutral axis. So you remember the distance between the neutral axis and A is 5. Or just look at here. So 15, the neutral axis is 10. Therefore the distance is 5. So C is equal to 5. I, we determined the I as 10,000. Here we determined the I on the section 10,000. Therefore the result is 4.2 Newton over millimeter squared. So this means it is 200 kilopascal. We determined this bending stress acting on point A. We also had torsional T, where is it? We also had this Tx, and that causes torsional stress. Tau for torsion, it is equal to T times C over J. I looked up for the polar moment of inertia of a rectangular cross section, and it is J is equal to BH in parentheses B squared plus H squared over 12. So what is T? Let's calculate the J first. B was equal to 15, 20 for H, 15 squared plus 20 squared over 12. Just calculate it. It's 15,625 millimeter to the power 4. What we have determined T as Tx, torsional load, torsional moment, is 400. Actually, this is not the formula that is used for a rectangular cross section. This one is for circular cross section. But determining the shear stress, torsional shear stress on a rectangular cross section is a bit complicated. So we just approximate the value by using the one for circular cross section. So we take C as 8. So assuming this was a circular cross section, and the value here, distance of point A to the center of the rectangle is around 7/8, so I take C as 8. And doing the calculation using this formula, so the result is 0.205 Newton over millimeter square. So it is again tower torsion. This is 205 kilopascal. So what were the other stresses? From shear stress we obtained 37.5 kilopascal. This is shear stress due to shear load. Torsional shear stress is 205 kilopascal. Now we have determined all the stresses acting on the point A. Now it is time to plot them on a stress element. We have started here, but it will be small, so we cannot fit all the values on this cube. I plot another cube, a bit larger one. So the shear stress caused by the shear load, let's say, let's call this tau V, and we had tau V here as well, complementary one. Also, and tau V is equal to 37.5 kilopascal. What else did we find? We found bending stress 200 kilopascal. And where does it act? The bending stress. So where is the piece? Okay. Here you see this was the bending. So that means at this point, which is above the neutral axis, there is tension. Therefore, this 200 kilopascal is out to the outside of the cube, like this, and call this, so this is not tau, this is sigma. Sigma equal to 200 kilopascal. And there is a complementary one on the other face, on the opposite face. So that the element is in static equilibrium. So now the third stress that we have found, it is the torsional shear stress. The shear stress caused by the torsional moment, in other words, and we determined it as 205 kilopascal. Tau torsion, say. And where does it act? If we look at this section and the point, this was trying to rotate. This one is doing the reaction like this. Also, this segment is rotating it like this. So there is the stress we have found is in this direction. I draw it here. If it is axis of rotation, the rotation is like this. So the stress I determined is in this direction. So it has got two components on Z and Y axis. This is X axis. So two components on Z and Y axis. And so what was the value? 205 kilopascal. Assume that this is just 45 degrees. The stress direction of the stress is 45 degrees to the y-axis, and then the components would be (145 kilopascal). So I plot it again. This is the original torsional shear stress, 205 kilopascal. So it is Z component, this is Y component. These are each 145 kilopascal. So we add this 145 kilopascal. So again the complementary one. Also there is this shear stress on this direction, and the complementary on the other face. Let's put the tau v's in the place. 37.5, 37.5. Now I had, so let's use different colors. For normal stress on the cube that came from bending stress, it is 200 kilopascal. So on the other face we also have the complementary stress. For the shear stress on Z axis, by the way, we should plot the coordinate system here. Z, X, Y. On Z direction, the shear stress we have got is one came from the torsional shear, 145. The other came from the shear load, is 37.5. The result is 182.5 kilopascal. So let's use green color for this, for the shear. So what is it? 182.5 kilopascal. And I plot on the other face the complementary one. Okay. And finally, the shear stress on y-axis, and it is equal to 145 kilopascal. We have to plot the complementary one on the other face. Okay, now we have completed the stress element at the point A. So what if the material fails at this point? The failure is due to the stresses that we have determined. And by the way, these shear stresses have complementary stresses on the other faces that we don't see. So if we want to plot in dotted lines, so there is red one here, and also this. for the other shear stress. Okay, now we have completed the stress state of point A. Thank you for listening.